Assalamu alaikum dear students. Welcome to seismology. As you all know that we have discussed the basic seismology in plate tectonics in our previous lecture. So moving on from plate tectonics, if we have plates that are bumping and grinding against each other, there's different types of boundaries that are going to exist between plates, and there's three types of boundaries that we are going to talk about. One type of boundary is what we call is a transform boundary. So these are boundaries where plates are just grinding past one another, one's not moving up or down relative to the other. Another type of boundary is a divergent boundary. So this would be like in the oceanic ridges or the spreading ridges, where new crust is being created and pushing the old crust out of the way. And then we have convergent boundaries. So these would be like the mid-oceanic trenches or like the Cascadia subduction zone, where we have one boundary that's being pushed or subducted beneath another boundary, which is riding on top of previous boundary. So these are three types of boundaries: transform, divergent and convergent boundaries. So talking about divergent boundaries, if I have a divergent boundary and I have oceanic crust, and an example of that would be like an oceanic spread ridge or a mid-oceanic ridge. You can think for a moment of an example of divergent boundaries, where I might have a continental crust. This is kind of a tricky problem, so think about it for a minute and see if you can come up with a place in the world where we might have a divergent boundary, or even more fun, go back to the figure that shows the different plate boundaries and see if you can find a place where you have a divergent boundary, but it's beneath continental crust. Okay, so you had a chance to look at a great example of continental crust divergent boundary is like the Rift Valley. So this would be, for instance, like the East African Rift Valley. So if you read, for instance, the book by Michael that takes place in the East African Rift Valley. So what's going on is you have a giant valley that's forming, where here's one plate, here's another plate, they are pulling apart, and you have all this sediment and rock in between, and as they pull apart, it's going down, and that's where in places like the East African Rift Valley you have lots of gas, like volcanoes, because this is actually pretty close to the mantle. So let's talk about the convergent boundaries. So we have an example, or you guys can think of an example of a convergent boundary that's oceanic and continental crust. That would be like a subduction zone. So maybe like the Cascadia subduction zone. What if you have a convergent boundary where you have oceanic and oceanic crust converging? Then you get a mid-oceanic trench. So this would be like a Marianas Trench, the deepest trench in the world now. So here's your challenge. You can think of an example where we might have continental and continental crust converging at a plate boundary. So if you go back and look at the plate boundary figure, and take some time and see if you can find the location when you get back. So hopefully you will able to look at the plate boundary map and try to find an example of continental and continental convergent boundaries. So if you get that type of boundary, you are going to get big mountain ranges, and that's a great example of big mountain ranges are like Himalayas. So eastern India and Nepal, that region, that's an area where you have two continental crust, they are converging. So we have plate tectonics in mind. This theory of continental drift is that all of the continent used to be together, and in our modern day revelation, what happened is around 200 million years ago, the continents started separating, and as they started separating due to continental drift, they eventually led us to where we are in present day. So the scientists have asked what causes continental drift, what is the driving mechanism, and the answer is we really don't know. There's no way to know or to test it, but we have some theories. They are out there, and so for instance, one of the theory is the convection, and this is the theory that most scientists accept today. So the theory of convection is that you have a hot material that rises up to the top of the mantle, and the cooler material gets therefore pushed down to the bottom of the mantle, which then gets heated up and rises back to the top. So you get this circular current within the mantle, and that circular current creates friction between it and the asthenosphere and the lithosphere, which then drag and create movement in the crust itself. So that's the idea where continental drift comes. So the forces then from this theory that are contributing to plate tectonics and continental drift are first, these convection forces shown by the red arrows here, ridge push. So ridge push is where new material is coming out, and the new material has to go somewhere, so it pushes all the old material out of the way, and slab pull occur in the subduction zone at that, like the subduction zone boundaries. And what happens is the subduction slab gets pulled under and eventually gets caught up in these convection currents, and then the current began to just yank and pull it down, which then has a tense or pulling effect on the whole rest of the slab here. So now we are going to switch gears a little bit, and we are going to talk about different types of seismic waves that seismologists used to read to look into and understand the earth. Now in general there are two types of seismic waves. The first type of seismic wave, we call it body waves. So these are the principal types of waves that are produced when a giant amount of energy is released into the earth, like from an earthquake. These waves travel through the earth from emitting from their source, and they can also be produced from another types of events that release large amounts of energy, like volcanoes. Might notice mine collapse, atomic bombs, or asteroid collisions, anything you can think of that produces a large release of energy on the earth. The second type of waves are what we call surface waves. Now, surface waves are generated from body waves, but they are altered because of the physics and the shape of the earth. When the body waves reach the surface of the earth, the wave then change shape and form and begin traveling and emitting around the earth, kind of like the same thing that happens when you ring a bell. The waves start ringing around and around the bell itself, and that's what give you the ringing sound. Surface waves are like. So there's seismic waves, body waves that get trapped at shallow depth and travel around and around the crust. So instead of traveling through the earth, these type of waves travel around the earth, around its perimeter. Think of it kind of like a ripples on a pond. So surface, anytime you have body waves, you are going to have surface waves as well. So if you look at the shape or the types of the waves, then the first we look at the body waves. The first type of the wave is called P wave. The P wave is essentially a compression wave. So if you think of a pulse of energy that goes out, is just going to brute force push the material, which will push the material next to it, which pushes material next to it. So it's like a pushing wave or a compression wave. So when you have a compression wave, if it's similar to a sound wave, because that's what sound is, it's just a compression in the air of air particles. So because it's a compression wave, it can travel through all different types of media, including fluids and solids. And you can see I have here different P waves velocity through different types of material. P wave velocity is characterized by V is for velocity, and then has a little subscript p. As you can see, P wave velocity through air is 0.3 km per second. Compare that through with P wave velocity through rock, which is much denser material, 3 to 8 kilometers per second. The second type of wave is called S waves. So the S wave is like a shear wave. So instead of a compression wave, this is a wave of shear stresses that are traveling through a material, and they can be stresses in both the horizontal and vertical direction. Now because it's a shear wave, they can only travel through solids. Now S wave, because it's a back and forth horizontal motion, S waves are typically the most damaging type of waves. These are the type of waves that produce that back and forth in an earthquake that can cause a lot of damage. P waves can be damaging too, but they tend to be really quick, and then they are done. S waves keep coming and coming, and then they transform into surface waves, which keep coming and coming, and those are where the real damage comes from. Now if I compare P wave and S waves are definitely slower than P waves. The shear waves travel much slower than the compression waves, and you can compare that. For instance, compare the shear wave velocity into a rock. Shear wave velocity is V. Compare that with the compression wave velocity. It is pretty remarkable. So the two types of surface waves that we have are called love waves and Rayleigh waves. So a love wave travels a little bit like a sidewinder snake. If you take a moment and go look at the YouTube video, like a sidewinder snake, and see how they travel. It's really freaky and crazy, but that's how love waves travel around the earth. As well as they are formed by the interaction of horizontal S waves and soft surface layer, so they kind of get trapped to those shallow depths. Now the Rayleigh waves are more like rolling ocean waves. They kind of roll and move up and down. So if you have ever been in an earthquake and you have looked up and you have watched the ground, and it's look like it's rolling like the ocean, so you are looking at Rayleigh waves, like really big Rayleigh waves, and these waves are formed by the interaction of P waves and vertical S waves. So you can see Rayleigh waves are really useful for engineers and for seismologists because we can characterize them really well. They can go pretty deep into the soil or the rock, and we can characterize them pretty easily, and based off Rayleigh waves we have used geophysical methods to predict the layering of the earth or the layering on the soil. So surface waves themselves, love waves and Rayleigh waves typically govern earthquake acceleration. So when you are at a distance greater than about 50 kilometers horizontally from the source, so this would be the epicentral distance, and we will talk about this in our next lecture. But if you are more than 50 kilometers away from the source of your earthquake, generally these surface waves are going to govern. If you are closer than 50 kilometers, then your body waves are going to produce larger accelerations. So how do seismologists know and interpret what's going on in the earth? Well, we look at the reflections and refractions of waves. We can use physics to understand how the various density of material in the earth are going to curve and reflect waves, and based on that we can determine not only the layering of the earth but the density of those layers as well. So we know now from the seismology that why the earth is composed of a liquid core, for instance, and is based of interaction of P waves and S waves. If I have a source here where it says 0 degrees and I emanate an earthquake or some sort of energy release, it's going to produce both P and S waves. And those waves, as they start traveling through the earth, but as they start traveling out and get into shallower and shallower, and not shallower but less dense materials that travel to the surface of the earth, the waves tend to refract and bend upwards, but you can see the pathway of these different waves going through different instances of the earth. But now if it's interesting, because what we find is that if I have a box recording instrument, maybe right over here on this side of the earth, and I know the exact instance when my earthquake occur over here, there is a zone in the earth where if I'm listening, I don't get any recording. So if we call that a shadow zone, and the shadow zone only will record P waves, I'm sorry, in the shadow zone no body waves get through because they get reflected. When I'm talking about the shadow zone, no body waves make it into the shadow zone because the waves are refracted and reflected. But then once I leave the shadow zone, which is at the angle about 140 degrees, what I end up seeing are only P waves, no S waves make it over here. And we call this the S shadow zone, and the reason No S waves make it over there because the S waves can't get through the liquid portion of the core of the earth. So they get filtered out, but the P waves can get through the liquid portion of the earth, and so because of that the P waves can travel through and get into the S shadow zone. So how do we use this information then to locate where an earthquake occurs? And you have probably seen this, right? And when an earthquake happens, how do we know where the earthquake emitted from or where the earthquake occurred? So we are going to use a principle called triangulation to try to determine where the earthquake originated from. So if I look at a single seismograph station, it's going to record the arrival of the various types of waves. So a trained expert and a trained seismologist can look at a recording from a seismograph and can say, you can look at it and say, there's the P wave arrival and there's the S wave arrival. And so they know when these waves arrive at different stations, and then using this information and understanding, and if we have some understanding about the mass or the density of the material through which those waves travel, we can calculate the distances between or the distance to the seismic source. So we are going to use this equation right here. I don't have that equation here on the slide, but I will share with you guys later during the online class, and we can discuss that equation in detail. So from that equation, essentially then when we get is, if I have my seismograph and I get a radius all the way around my seismograph, I don't know where the earthquake occurred exactly, but I know it had to occur somewhere along that radius. So it's like drawing a circle around it. So the way then that we can find the exact location is that when we use multiple seismograph or multiple seismic recording stations, and we start to overlap the circles, where all the circles overlap, that's where the X marks the spot, that's where the earthquake emitted from or occurred. Or so we are going to use triangulation to identify the location of the earthquake. So we need at least 3 recording stations. To do this, we prefer more and more recording stations. We have the more accurate our estimate of the earthquake. So that would be all for today's lecture. Thank you so much for participating, and wish you a wonderful weekend. If you guys have any questions, you can reach me through this email. Have a wonderful weekend. Thank you.